I'd like to move on now to the next section of our meeting, which are really to share with you some deeper research talks. And our first presenter is Monroe Kennedy. Monroe is an assistant professor of mechanical engineering. He has come to us recently from the GRASP lab at the University of Pennsylvania and has already made an impact with starting his own research lab and with teaching a brand new course on modeling control that has gotten rave reviews from the students who've taught it. So really happy, Monroe, that you're able to join us here and introduce yourself and your work to the affiliates. Thanks.
Thank you very much, Chris. So yes, I'm an assistant professor in mechanical engineering, and I direct the Assistive Robotics and Manipulation Laboratory, the ARM lab. A little bit about our lab. We're really focused on the intersection of people, robots, performing complex tasks. We have three main domain areas: robotic assistance, connected devices, and intelligent wearables. You can think of robotic assistance as being corporeal systems that can operate alongside a human counterpart, possibly doing service tasks for them. Intelligent wearables are robots that are connected to the person, but in order to interact with the environment, the human has to communicate their intent and their action, their desire through the robot. One would be a prosthetic. You could even think of a vehicle as being an intelligent wearable. You want to move somewhere. How do you communicate your intent to go somewhere through that vehicle? And then connected devices, which are more so passive, but still have to have situational awareness and anticipate service needs. So we look at this problem, right? Traditionally, you have robots that are doing complex tasks, and we were building up this ability. But now as we reach this sort of critical stage, we realize that a lot of times robots are going to need to work with human users and collaborators. So to be effective, the robot needs to be able to model itself, whatever task it's trying to complete, as well as the human in the loop as well. Over the last year, I've been very fortunate to bring together an amazing team, many of which will actually be presenting student posters today. I really encourage you to check them out. I'll tailor this talk on intention and collaboration towards autonomous vehicles. But what I hope comes out of this is really realizing that the fundamental techniques for collaboration and intent estimation can be used across many domains. And so I hope you can see in their work how what they do may even be of interest to the work that you have. So the questions I want to talk about today, right, is first, intelligent vehicles and collaborative robotics. So can intelligent vehicles be improved by modeling and anticipating the driver and the environment? For parallel and shared autonomy, if people want to drive, which I know I personally will never want to stop driving, when does the robot take over control? And how is control safely returned? And then finally, for predicting human intent and actions, how can human intent and actions be modeled and leveraged for predictions? So throughout this talk, I'm going to tie these questions together, and hopefully you'll see that these actually naturally flow together. So starting off, right, can these intelligent vehicles be improved by modeling and anticipating the driver and the environment? To begin to answer this question, I'd really like to go back to a version of the chart that Chris showed at the beginning, where collision happens at T0, here shown in the bottom corner. And if you kind of noticed, he actually had a sort of semi-log, one-dimensional semi-log plot. My second dimension here is if you have some algorithm that's executing a strategy, what is the complexity of that algorithm or approach? So you could say, you know, around collision, either right after collision or on the onset of collision, you know, airbags can typically deploy within 30 milliseconds. A lot of the newer vehicles, intelligent vehicles, are able to employ emergency braking, which allows them to at least reduce the impact in some cases. And that happens about on a quarter of a second timeline. We have this ability to think about risk negotiation. If you have a vehicle that has a higher level of autonomy, it might be able to detect a risk much further out. And if it can, it might be able to alert the user about that risk. And this is a particular project that is of interest to my lab. And so around this time, you see here in our log plot, This is when an intelligent vehicle might be able to detect potential danger. Another beyond this imminent danger timeline, you also can think about long-term driver monitoring. So here, if the driver is beginning to fall asleep or woozy, what can you do to ensure that the driver is attentive if that's necessary for your vehicle? And then even beyond this timeline, not going to the weeks and months, but even on the matter of many minutes, hours to days, you have the self-diagnostic tools that might be able to detect if there's an internal problem, and that can be very useful when it comes to predicting if the internal vehicle might have an issue that could lead to an accident. So for collaborative robots, I'd like to claim, if I can, this entire region right here, from the emergency braking stand to even long-term driver monitoring. And so what is this collaborative robotics, and how does it fit into the timeline of robotics overall? So if you think about the early 80s to the 2000s, there was a lot of focus on automation. How can we make these robotic systems do repetitive tasks with precision and accuracy? We began in the early 2000s to have autonomy. Here is actually an autonomous vehicle from the Vail lab. Here you see the Stanford logo. This was the onset. Now you have these systems that need to be precise, accurate, and they also need to be able to operate in unstructured environments. Then we saw the onset of centralized swarms, here shown as a light show at the Olympics with Intel. And here they have many drones flying together for this light show in a massive coordination strategy, but it was centralized. And then you have large systems here, the Amazon Kiva robots that, again, operate as a swarm, but now there's no necessarily one centralized controller telling every robot at every moment what to do. Robots locally know what they need to do and they communicate through some oracle, but the control is in fact decentralized. So you see this procession, right? We have autonomy, precision, the centralized swarm, decentralized swarm. Now, what if we replace one of these decentralized systems with a human? How can the robot work effectively alongside a human counterpart and be safe and accurate and optimal? So if we want to set stone this into the driving problem, you can think of the robot as being an intelligent vehicle, the environment as being the task that is of interest, safely navigating your environment in a timely manner. And the human in the loop, if you're performing some sort of shared autonomy, is the driver. So if we think about parallel versus shared autonomy, the question again is, if people want to drive, when does the robot take over control, right? And if the person wants control, as you see here, motivated well, in iRobot, how can control actually be safely returned? And I like this clip particularly because in this instance, you might have the desire to take over at high speeds and not at a stoplight. So there's a lot of things we need to think about if we want to do this sort of thing safely, reliably. So I'm making this distinction here between parallel autonomy and shared autonomy. And this is a local definition. So I want to make this sort of define this term of shared autonomy to be very explicit, that in parallel autonomy, you might imagine that control transfer might kind of go one way, that the human and the robot may operate without interference. But in shared autonomy, I really want to capture the idea that there's a blendedness in the control and operation. And so control can go from the human to the robot or from the robot to the human. And this concept is not even lost necessarily even on the definition of the levels of vehicle autonomy. So I'm sure all of you are very familiar with this chart. Particularly, I'm interested in conditions 3 and 4, where you have this very capable autonomous system that is able to monitor the driving environment, but it expects that it might need to or might want to transfer control to the human and at times take it back. And the main difference between 4 and 5 here, in my mind, is just, is it possible for the human to ever take over control again? So here's a very simple sort of control loop paradigm for for you. So here you have some input from the system, the environment, you have the autonomous vehicle, you have the driver. When does the vehicle know when to take control from the human, and how do you safely give it back? And if you're negotiating that control or arbitrating that control, how do you present the potential risk to the human driver? And then how does that influence your plant, the vehicle, as it's in some environment? So two questions I think that kind of really immediately follow from this are, what are the risks from arbitrarily taking control from the human? And what are the risks for giving control back to the human? So to answer this first question, I think the main risk to the vehicle is, does the vehicle have an accurate model of plant dynamics, right? So there's amazing work being done by Chris Gerdaus's lab, particularly, in thinking about how vehicles can actually drive on low friction surfaces and modeling these types of environments. Here, it's really hard to have really good analytical representations for these types of environments, yet it's able to do a good job. So what if they were to drive on an environment or a ground that they had never seen before? Maybe a human might be really good at adapting quickly to a new type of environment or condition, and the robot needs to observe this and make sure that its plant dynamics are accurate before it takes that control from the human, if it's never observed that exact situation before. And going the other way, does the human have an accurate internal model of the plant dynamics, the vehicle, and effective control strategy as well? An example for this would again be, you're on the highway, maybe it's raining and there's a curve, right? The robot, the vehicle knows what the dynamics are and effective control strategy to maintain control in this bend. But if the human doesn't actually have that same control strategy, turning over the control to the human in such an instance, especially at a high velocity, could be catastrophic. And so before you do this, you need to ensure that the human has an adequate plant dynamic model and an effective control strategy. And so I postulate that one way to think about this is to actually model human intent, right? Where do they want to go, right? And if you know where they want to go, then also, and this kind of correlates to the plant dynamics, what is their action strategy to get there, right? What is their control strategy? This sort of arbitration example, I think, is also well motivated in a scenario like this. So here you see in the bottom figure, you have a person driving forward. The robot is getting ready to give control back to the human. Will the human stay in their lane, or will they swerve, right? So there's a safe set, which is your lane. You see here on the right-hand side. And if you imagine, traditional, switching control strategy, this is just Boolean. Vehicles in control, and at TS, you switch and give control to the driver. But what will the driver do, right? Will the driver stay in the safe set, or could they possibly diverge, which, again, could be catastrophic? So another way to think about this, right, is instead of going cold turkey in a Boolean fashion, what if you were to ramp up control from the vehicle to the driver? And so then the question becomes, okay, this probably from an implementation standpoint isn't really hard to do, but what should drive that transition rate between the vehicle and the driver? I postulate that, in fact, you might want to really think about their intention model, that action model. And if it conforms with what you believe it should be, then you can hand over control in a very safe and meaningful way. A great example I like to give for this is if you ever played any racing games, Mario Kart or others, where you're following a track that's well defined and you're trying to beat your own best time. You can see that as you're trying to do the optimal path and minimum time as you go around the path, ultimately the turns that you make, if the path is not, or the track is not very symmetric, the turns that you make will begin to converge, and there'll be very little variance in where you are and where the ghost was from your previous run. And so what ends up happening is your state as well as your action inputs begin to converge. So if the robot knows the environment, the track really well, then given those conditions, if its objective function for the human and action control strategy is the same, then it knows what the human should probably be doing at every instant in order to be successful. And so if you can do that and you can feed that forward, if the human's actions conform with what you believe they should be, given your understanding of the environment, then you can have that trust and turn over control in a meaningful way, in a safe way, to the human driver, and have a high potential of remaining in a safe set. So we see, hopefully I've motivated well to you why predicting human intent and actions is extremely important. Uh, so how can we actually model these and leverage them for prediction? So the first point I want to make on this note is that human intent is never truly known by an observer. It can only be approximated. And to kind of intuitively make this argument, here, consider this little taxonomy where you have the human's action model as well as a human intent model. The action model is your control strategy. The intent model can be thought of as the objective function. So this is an observer. You're the vehicle thinking about the human, right? Do you know the action strategy of the human? Do you know the control objective, right? If both of these are known, you might have very high trust. The human intends to stay in the lane and can control the car to do so. If you know the fact that the human is able to drive, but you don't know what they're trying to do, the human may intend to stay in the lane, but they might not have the control authority or knowledge to do so. This could be like a novice driver, for instance. So you know the objective, but you're not sure if the human has the action or control strategy to achieve it. And then vice versa, right? The human could be completely capable of staying in the lane, but veers away, right? That could be thought of as, imagine like a driver that is driving aggressively on the road. You know they know how to drive, but there's a safe actions, and they're taking actions that you wouldn't expect. And then finally, the last case is, neither, right? And so that's the risk. And so, right, hopefully we can delineate this in your mind a little bit to think of human intention prediction as being two things. One, right, what is the objective and the constraint that the human has? And two, right, based on that intent, what is their action and control strategy? And so to really understand this objective constraint and action from that previous chart, we're really looking at this. How do you expect the human to interact with the environment, and what does that inform your internal model about the human and the environment, and how you should transition control? So I'd like to talk about shared autonomy within this sort of transition or arbitration as thinking about how you can actually safely and smoothly transition that control. And it might be important to negotiate or arbitrate that control. And I think it'll be fundamentally conditioned on interagent trust, where I'm defining interagent trust here as A, the collaborator, here the human, if you're the robot, action model is known, right? You know that they can drive. And two, the collaborator's objective function is sufficiently close to yours. You agree that the human wants to stay in the lane, which is the safe set, which won't cause collision. If you know these two things well, then I believe you can characterize interagent trust. And I cast it in the context of the vehicle here, but I encourage you to sit with that a little bit and even think about that in even more broader sense. When you have collaboration, this sort of trust is conditioned on these two things, right? Do you understand how they're able to act? And then is their objective the same? If either of these are not true, you might be hesitant to actually turn over control to a collaborative agent, or even share a lot of control with a collaborative agent. So again, right, this brings us always back to, okay, predicting the human's intent and action based on the environment, and even actions that the robot has taken in the past, is extremely important, right? And so I and my student, we constructed this very brief literature review that really overviews a lot of methods in intent estimation, as well as their coupled approaches for shared autonomy. And here, a lot of these may seem very familiar. Bayesian inference for predicting actions conditioned on, for instance, what the other agent is doing, the environment, hidden Markov models, how does the state transition, POMP-DPs, discrete, continuous, how do those scale? You have the curse of dimensionality. There's been a lot of amazing work, even work by Michael Kokendeffer, on how to think about this in terms of a continuous space, and even extending that, right? We're thinking about using generative models to help with the reward output and observation output to make these more applicable for continuous states. And even max entropy, inverse reinforcement learning are all approaches that we can take to begin to address this. And so these are the references that match to that table. But actually, I'd really like to focus on a paper that actually came out of Marco Pavoni's lab this summer. I've been quoting this a lot. I love this taxonomy that they built in this chart. And they were really talking about trajectory forecasting in this paper that they had. And they broke down all of these different methods, right? So if you're trying to model the human, right, in their case, they were thinking about, a trajectory that the human would follow. They were asking, okay, what if you have an ontological method? So you think there's an underlying core structure. This can be valuable if you know the system really well. So if I'm thinking about a dynamical system, let's take a car again. Maybe a bike model works really well. But then when you begin to think about humans and how humans make decisions, that's really dependent on the human and whatever it is they're trying to do and what the other players are. And so data-driven approaches really rise to the top as being a competitive way to think about this. And particularly, you want stochastic methods, methods that can associate the uncertainty that is present when you're trying to predict something you fundamentally don't know. And this makes generative approaches rise to the top as a very competitive way forward. And so keep that in mind. You may see this in like terms such as conditional variational autoencoders, but these are very powerful tools that we can use for this type of approach. And so within this sort of predicting intent models, I want to present this sort of last idea slide here. So if you think about what you need to know as the robot, right? You want to know, how does the human make decisions? How do the actions of the human condition on the state of the vehicle, the observations of the environment, as well as actions that the vehicle may have taken itself if they were actually performing some sort of shared autonomy. Maybe if there was some sort of switching, how did the actions of the robot, the environment, and the vehicle itself play into how the human makes their decisions, right? How do you model that? There's some dynamical model for the vehicle itself that's conditioned on actions that the human has taken, actions that the robot has taken. And even for those where it might be kind of hard to think about this, a very simple version of this is actually cruise control, right? If you have, let's say, the vehicle controlling acceleration and the human controlling steering, or vice versa, right? Here is a very easy and quick example to show what this sort of function might actually look like. And finally, what is the robot's action policy, right? How does the robot make decisions based on the vehicle, the human, and the observation of the world? So a few takeaways from this, going back to our original questions, I believe absolutely, right? If you can have a robot that can model the driver and environment, it has the potential to improve both safety and functionality. When does the robot take over control? Takeover may easily occur when it's requested or when it detects a critical risk. And then how can it be safely returned? If you can model the human's intent and action model, then the robot can predict the expected human input during control arbitration. And finally, how can human intent and actions be modeled and leveraged for predictions? I think a very promising approach is generative approaches, stochastic modeling for trajectory and action prediction, coupled with continuous implementations of frameworks such as IRL or POMDB for intention and action forecasting. So in the remainder of this presentation, I'd really like to show you how the research that we're doing in the ARM lab is beginning to address some of these concepts, right? And so the ARM lab is conditioned on problems that fall within this domain: robot, task, human. How do we make these situations work together? The first one that I'm going to discuss is actually dexterous manipulation. So particularly for humanoid-esque sort of platforms that can perform manipulation, you need to make your hardware better, right? It's really hard to have good algorithms and capable systems if their hardware is not good. And so this is a fundamental setup for that. And it actually uses generative approaches to then say, if I'm touching with a dexterous fingertip, can I detect friction in the contact that I'm doing? And can this actually improve my manipulation strategy? So we're looking at cutting edge approaches that allow us to increase the dexterity of robotic hands. And all of this sort of research actually ties together. So this project directly informs other projects that actually do combine human in the loop as well. So another project that we're working on is human robot cooperative transport, this in collaboration with Dorsa Sadiq and the CS department. And here you begin to see some of those elements that we discussed before. If you have a human and a robot carrying an object together as teammates in a cluttered environment, the robot needs to be able to predict if there's not explicit communication, implicit communication. The robot needs to predict where a human teammate wants to go and negotiate that as they go through an environment. So there needs to be interagent trust, right? There needs to be intention modeling, action modeling in order to be an effective teammate. And so we're doing a form of transfer learning, observing how humans do this together, and then applying this to a robot-human pair. We have a robotic assistant for a first responder. This project has a few components, but the one I want to focus on today is when you're trying to move boxes from one location to another and the robot is helping you. If the robot is able to model the human, if the human is suboptimal, maybe you carry very heavy boxes, the robot can then say, I should carry the heavier boxes, which will then make the human carry lighter boxes, which will then benefit some overall optimal strategy, let's say moving the boxes in optimal time. And so if you observe the human over time in a long sequential task, can you model their behavior and then take action, not as a competitor, but as a teammate that makes the overall team more efficient? For the Intelligent Prosthetic Arm project, which you see today, it's actually the first project in the student session, is saying if you have a prosthetic arm that's a full prosthetic, so the person has a shoulder disarticulation, can you use EMGs and mixed reality to allow the human to convey a complex intent in terms of what they want to do in their environment? So then this would be, for instance, telling the human, hey, I want to pick up this cup, right? And I want to do that with fine manipulation and a dexterous fingertip. Can you convey that intent to the robot when you're using EMGs and your control signal is not that good or low dimensional? For the Smart Belt and Path Prediction project, which you'll also see in the second session, here we're just saying you have a passive device that's sitting on the person. As you're walking in an environment, can it observe where you're walking and predict with high certainty where it expects you to go? Ultimately, we want to use this for lower limb exoskeletons, but we immediately recognize that this could be very useful for fall prevention in the elderly or visually impaired. And finally, this project, Leveraging Human Intent for Shared Autonomy, a lot of the components of this project I actually discussed earlier in the talk, but the idea is, when you need to negotiate with the human, right, this really intelligent level 3 and 4 vehicle sees the environment, sees a risk. Can it tell the human, hey, I think there's a risk coming up? And if the person is paying attention, you can let the person remain in control. If the person is not, then you may want to transition control away from that person or have some input that mitigates that risk further. And then, also by communicating, right? This is the communication. By communicating with the person, can you even determine if it's safe to leverage, safe to give control back to the human as you're modeling their intention and actions? Thank you very much.
Ah, there we go. Actually, a question from John. How important are sensors for your work?
I think they're critical, right? There's the paradigm between the robot, the environment, and the person. You need to be able to sense the environment so that you can have a really good fidelity model for the environment, and you need to be able to detect the person as well, right? So how do you get that information from them? Some of that might be directly through a control input, but others might be if you want to have an attention model, you may need to observe where their face or their eyes, where they're looking. So very important.
Good, Monroe. Since you put up the bullet point of sort of the two criteria that you have to basically understand the other agent's capabilities and share intent, I've been sitting there trying to think of a counterexample going, it has to be more complicated than that. And I have to admit, having thought about this since you put that slide up, I can't think of a counterexample. I really love that framing. Can you just explain a little bit about some of the experiences that you had that led to what I think is a very crisp framing of these issues?
Yeah, so I think you're referring to like the interagent trust definition. Yeah. So I was very excited actually earlier this year when we came up with that, because it's very simple and elegant, but it's rock hard, and I think it just applies to a lot of different scenarios. But I think again, fundamentally, I think it sits in foundational controls, right? What's your objective function, right? And then even if you have a good objective function, do you have a good control strategy to reach it? Right. And so apart from any other agent, just that's what it takes to reach a target. You have to have a good objective function and a good control strategy that can leverage that objective function to reach it. And then when you come to trust, right, if you have some alternated control, imagine you had a singular objective, but you had to alternate control at some defined frequency. You need to have a same and shared plan. And I think this goes back to the sort of swarm notions, right? And decentralized control. If you have that shared objective, right, and you know that the control strategy is aligned, right, then you can actually have cooperation. And so you're fundamentally basing that on, that effect. Can you see those two things in your collaborator?
Excellent. So I'm going to actually abuse the timeline by about a minute here because Lynn asked a good question from Ford in the chat. Actually, Lynn, would you mind unmuting and asking that? Because I figure we'll ask this question, then we'll move on to our next speaker.
Hi, Monroe. Yeah, I was asking about the control of the vehicle during the changeover from machine to human. If the vehicle isn't responding properly to the human steering wheel commands, what prevents them from oversteering and going into an unstable loop?
So I'll rephrase the question to make sure I understand it. So your vehicle is transitioning control to the human, right? And while the human takes over, right, there's not a good mapping between the steering inputs from the human and whatever control strategy the vehicle has, and that could actually cause an accident. Is that what you're saying?
Well, yeah, because the vehicle may not be fully responding to the steering wheel position as set by the human. They will feel that it's not properly responding and oversteer.
Yeah. So this I think goes into, and we still have to work out all the details, but I think this goes into that sort of blended control strategy. So the example I like to give people is, again, back to that game. When I was a kid, I used to play the racing car games with my uncle. And I sometimes, if he put the controller in my hand and I think I'm controlling one of the vehicles, I wouldn't realize that I wasn't driving until there was some turn and I would make a mistake and the autonomous vehicle was doing what it was supposed to do. So the point I want to make here is, for the initial component, you don't even necessarily need to give the human the control authority. You just need to observe the inputs that they're giving. And if those inputs match what you believe they should be doing, then you begin to transition that control to them. If it's overshot, right, then you can even, if you have some two-way communication, if you have, the ability to give some haptics information back, you can negotiate and help them adjust their model, but you don't have to give control of strategy over unless you believe that those inputs match what you think they should be.
I see what you mean, because the first couple of times I accidentally tried to steer while lane keeping was engaged in my vehicle. It was confusing because it wasn't responding properly.
Yeah.
Great question, Lynn. Thanks for that observation. It sounds like a fun project, something we could code up on X1 and go out and try and see how people respond to that. Monroe, thank you very much for sharing this. I really appreciate it and appreciate all your contributions to our initiatives in CARS here.